Hi everyone, this is Mr. Zarzak, and in this screencast I am going to take you through the velocity equations notes and show you how we derive physics equations graphically. Okay, so this little template has several pages, so I'm going to be moving around between, jumping around between the pages as necessary, so just so we can keep track here, that's page number 1 up there. Okay, we're going to call this one page number 2. This is page number 3. And then down here, this is page number 4, okay? I'm actually going to be starting on page number 2, okay, so please fill this out with me. What we're looking at here is a velocity time graph. There's some numbers on the axes just for talking points. Really, we don't need any numbers to derive the equations that we need, but it'll come in handy. All right, so just looking at the graph, okay, we can see that as time goes on, okay, the graph goes up and to the right. The fact that this is a straight line means that we have a constant slope, okay, and that's going to become important later on. Just conceptually, just real quick, all right, at time 1 second, okay, there's a velocity of 1 meter per second. All right, at time 2 seconds, there's a velocity of 2 meters per second. Okay, so we're going up by equal intervals. And so we say that the slope is constant, the rate of change is constant here. All right, so there's a couple of points I'm going to put on the graph. Let me just make this a little thicker. Okay, so like this is where we start. All right, and then the graph goes up to here like this. All right, up until now we might have been calling this like V1 or V2 or T1 or T2 as an ordered pair. Okay, so some new terminology. All right, I'm going to label this as VI. Okay, where the I stands for initial. All right, so that's just a way that we signify starting. Okay, and then this point up here, I'm going to label that as VF, so that's final or ending. All right. The initial velocity is at 0, so that just means that we start at rest. So think like if you have 0 motion, it just means you're not moving. All right, at time 6 seconds, where we have V final, we're at 6 meters per second. So we've changed from not moving to moving. Okay, that requires acceleration. We'll come back to that. All right, there's two values here for VI and VF at 0 and 6, okay, and so just like we would with any other numbers, we can take and we can compute the average of these two numbers, all right, and since these variables represent velocity, what we're really talking about is computing average velocity, okay, and so we take V initial plus V final, so we take two numbers, add them up, and divide by 2, okay, so that's just arithmetic mean or average. In fact, I think just for convenience sake, I'm actually going to change this to, let's make this green. Okay, you'll see why here in just a second. My initial velocity here, you can see the point right on the graph, it's at 0, all right? And so it's like it's not even in the equation, like it just factors out like that. Okay, and so this simplifies down. All right, what I have here is average velocity in this case is just equal to the final velocity divided by 2. If I zoom out to the graph, okay, well, final velocity, all right, the value of the velocity at this VF is 6 meters per second, all right? This little equation that I've written, VF over 2 is equal to V average, okay, it tells me that if my final velocity has a value of 6, well, then my average velocity, which is be half of that, so 6 divided by 2 is 3. Okay, if we think about where that appears on the graph, look at this, all right, it's right here, right smack dab in the middle. It's almost like we can think about this as like going up a hill, okay, and when we reach the midpoint of the hill, that's the average height, okay, but I'm not talking about height now, I'm talking about velocity, all right? I can take this same relationship over here, average velocity is equal to final velocity divided by 2, okay, and if I just do a little bit of algebra, I can manipulate it to get that 2 out of the denominator, okay, and then I'm just going to take and I'm just going to rewrite this because this is going to be a convenient iteration of the formula. So VF is equal to 2 times V average, okay? And that's kind of important. So I'm gonna circle this because this is going to come up a lot in class. Now, it's important to note that what I'm looking at right now is a graph that starts at 0 velocity, which means a graph that starts from rest, okay? But there's no reason, nowhere is it written that things have to begin from rest. There's things that are moving all the time. There's things that have been moving, okay, for eons here. And so I have another case, all right, if I scroll on to page number 3, okay, this is a case where the object, whatever it is that we're measuring, already has some velocity, okay? So what this says is, this says VI does not equal 0. That just means that we have some kind of motion to begin with. And you can see here on the graph, all right, that the initial velocity, the first point that I see right here, at VI, okay, has a value 1 meter per second. So whatever this is, it's moving at 1 meter per second, all right? But that motion does not remain constant. We can see that the velocity graph goes up. It has a non-zero slope. Okay, at the end of the graph period, okay, there's a point up here, so that's my VF. Okay, and you can kind of see that it looks like it's about 7 meters per second. So we wind up going a little bit faster than we were before in the starting from rest case because we had some initial velocity to begin with, all right? Now, if I do the exact same trick, okay, down here, where if I want to compute the average of these two velocity values, okay, I'm leaving them as symbols, but we're really just following the way that we compute the average of two numbers. We take them, we add them together, and we divide by 2. Okay, that right there is a very useful formula in physics. Okay, I mean, it's not even so much of a physics formula. Okay, as it's arithmetic mean. All right, it's just the average formula. Okay, so I'm going to take and I'm going to circle that too. So that's like the general form. If I have a non-zero velocity, okay, this is the way that I would compute the average. All right, so now I want to jump back, okay, to that previous page. So let's zoom back up. So I'm back onto page 2. Okay, because there's more to the story. All right, this is not the limit of what I can do. All right, we have been working with graphs, and the two mechanisms that we've done so far for interpretation is we look at the slope of the graph, and then we look at the area. All right, so in this middle column here, I am going to look at the slope of the graph. All right, and in fact here, just to make this neat and clean, let's take all this that we wrote here. Okay, let's just drag that down a little bit, just so we have a heading for what we've done here, which is compute the average. All right, and let's do the exact same thing, all right, down here. And move this down. Okay, and we just found the average. Okay, we're going to look at the slope here as well. All right, but first we're going to do it on page number 2. Okay, you'll see why here in just a second. Okay, so to compute the slope, if you remember from your math class, you were probably taught that the slope is the rise in the run, or the change in the y over the change in the x. Okay, and we will do that, but we're going to do it for the variables that are actually on the graph. Okay, so rather than look at the change in y over the change in x for the slope, we're going to look at the change in the velocity. Let's change colors here. Yeah, the change in velocity with respect to the change in time, because this is a velocity versus time graph. Okay, we have previously seen this delta v over delta t. That right there, the change in velocity with respect to time, that is the definition of acceleration. Okay, and that's kind of an important concept. All right, the slope of a velocity time graph tells us the acceleration. All right, that's important enough to where we'll write it down, but first things first, let's finish up what we've got to do here. If I take that delta v, I can take it and I can expand it out a bit. Okay, changes, take your ending value and subtract your initial value. Okay, and on my graph, my ending value is this thing that we're calling VF, or final velocity, and the initial value, we're calling it VI for initial velocity. Okay, take that and divide by the change in time. So we have some final time minus the initial time. Okay, my graph starts here at 0 seconds. Okay, so the initial time is just 0, so it's like it's not even there, and the initial velocity in this case is also 0, so it's not even there. All right, and so what we wind up with is this relation of acceleration in this case is just final velocity over time final, where the time final is just any point in time that we're interested in looking at on the graph. Okay, because we're going to start our clocks at 0, okay, it becomes unnecessary to label the time with the little f. Okay, so I'm just going to take and I'm going to rewrite this. Acceleration is equal to VF, okay, divided by t. All right, and then I'm going to get that time out of the denominator by taking and multiplying both sides of the equation by time. Okay, and then just to clean this up, I get this nice little relationship that says the final velocity is just equal to the product of the acceleration and the time. Now this final velocity term, okay, that's a velocity at some discrete point in time. This right here, this is your instantaneous velocity. Okay, well, the other day we defined the difference between average velocity and instantaneous. This is our equation for instantaneous velocity for the case where we start at rest. All right, but again, nowhere is it written that objects have to start at rest, so we have to consider the moving case too. Okay, and that's exactly what we're going to do. All right, we're going to find the slope of this graph. This is still just a velocity time graph. Okay, so the slope, which is the acceleration, is just defined as the change in velocity over the change in time. That's the rise over the run of the graph. All right, and I can take this and expand this out a bit in the sense that final velocity minus initial velocity, that's my delta, that's my change, or the difference between the two values. Okay, and my initial time here is still just 0. Okay, so when I'm looking at the change in time, it's really just tell me what time it is that you're interested in analyzing on the graph. All right. I can't factor out the initial velocity here now because it's not 0. Okay, on this graph it has a value of 1. All right, but what we're doing is we're deriving what's called the general form of the equation. I'm going to take and still going to factor that time out from the denominator like this. Okay, and so like over here on the left side, I've got acceleration times time. Time times acceleration is the same thing as acceleration times time. That's commutative property of multiplication. So I got v final minus v initial. Okay, and then I'm going to take and I'm going to move this initial velocity over to the other side of the equation. So another algebra step. So this is the derivation. Okay, so we're doing a mathematical derivation. Okay, and what I do to one side, I must do to the other. Okay, and so what I wind up with is initial velocity plus acceleration times time is equal to final velocity. Okay, and traditionally when we write this, we just flip it around on itself in the sense that we typically write it like v final is equal to v initial plus acceleration times time. This right here, okay, this is the full formula for what we call instantaneous velocity. This is a big one, okay, a real big one. All right, so big in fact, all right, that it's worthy of a place on the first page of these notes. So I'm going to zoom all the way back up to page number 1 where it says velocity equations and says how to read the equation. So I'm going to take and I'm going to rewrite this. All right, Vf is equal to Vi plus At. All right. And then underneath I've got a sentence with some blanks to fill in. All right, it says here, how fast I'm going depends upon. Okay, so when we look at an equation, okay, the idea is that when we say read the equation, it's interpret what the variables are telling us. Okay, so if I'm interested in how fast I'm going and which direction at some point in time, the things that I must consider, all right, in order to address this question is, 1, was I moving to begin with or to start out? All right, that's going to make a difference on how fast and which way I'm going at some point later in time. And I must also consider if my motion remained constant or if it changed. So did I speed up or accelerate in the other way, which is slow down? And if so, for how long? In other words, what's the time interval that I'm interested in? Okay, so I'm taking Vf equals Vi plus At and breaking it down conceptually into its different components. All right. Now I'm going to go back to that graph there on page number 2. Okay, I've considered the average value. I've considered the slope. Okay, I'm also going to look at the area underneath the graph. Okay, because if I look at the area, switch, let's do, yeah, that's a good color. Okay, so if I look at the area underneath the graph, okay, it's a pretty familiar shape. Let's make this a little, if I fill this in here, okay, I can see that I'm just looking at a triangle. All right, well, to compute the area of a triangle, okay, that's something that I learned back in geometry class, sometime in like elementary or middle school or something. Okay, the area of a triangle is just equal to 1/2 times the base of the triangle times its height. All right. Since this is a graph of velocity and time, okay, I'm going to rewrite that area formula using the variables, okay, that are actually on the graph. So let me show you what I mean here. So area equals 1/2, that's just a coefficient. Okay, the base of my graph down here, okay, that's just the time. All right, so I'm going to replace b with the variable for time, which is t. Okay, and if I look at the height of the graph, okay, well, the vertical axis of the graph has velocity on it. All right, and so my variable for the height, instead of writing h, I'm going to write v for velocity, and specifically, okay, this triangle, the height is described by this final velocity. All right, so I'm going to write this as VF. Okay, so I've just rewritten the area formula for a triangle. All right, now there's a little math trick I'm going to do here. I take 1/2, all right, times the time. All right, but I'm going to take that VF and I'm going to replace it. Okay, the reason I can do this is because if I just go over to the column directly to the left, I have this expression for VF. The final velocity, the instantaneous velocity, is equal to the acceleration times the time. And so I'm just going to take and substitute for this VF using AT. So I'm going to put in the 1/2 times T times A times T. So it's like I subbed out the VF and I replaced it with the AT. All right. And when I do this, look what happens. Get your colors right. There we go. Okay. I get this 1/2 times time times acceleration times time, which means this actually simplifies down to 1/2 times acceleration times time squared. All right. And this tells me something. All right. If I look at the units of this, I know this is pretty crazy, but the units of acceleration are meters per second squared, okay? The units of time are seconds. That's the standard unit of time. So if I take seconds and I square them, I get seconds squared. See, so it's like I'm looking at the units of this term, and I'm looking at the units of this term, okay? Well, if I take meters divided by second squared times second squared, okay, the second squared just factors out, and I'm left with these units of meters, okay? And that right there tells me what the area value underneath a velocity time graph really is all about. Meters is the units of displacement. Okay, and that's why I'm going through these steps here. See, when I compute the area underneath a velocity time graph, what I'm really finding is the displacement, which is how far you are from where you started. Displacement. Okay, that's an important concept. We're going to summarize all this in a minute. All right. Now, this little trick with the area, okay, this is for the case when we start at rest. But just like with velocity, when we look at slope, okay, we can consider the case where we're at rest, but we can't stop there. Okay, we got to be if it's really a physics equation, okay, it has to be able to describe all different types of motion. All right. So I'm going to take and do this exact same trick down here for the case where we're already moving. All right, so we're going to look at the area underneath the graph. Okay, now if I look at this area under the graph, all right, well, if I kind of draw it out, you can see it's a non-regular trapezoid, okay? Rather than work with that, I'm going to take and I'm going to break up this into two distinct pieces, okay? I've got a triangle on the top. All right, and then on the bottom, the last little chunk that's left over is just a rectangle. Okay, and I'm doing this because I know how to find the area of a rectangle, okay, and I know how to find the area of a triangle. In fact, I just found the area of a triangle on the previous page by taking 1/2 base times height and manipulating it, doing some algebra tricks to find this relationship of D equals 1/2 AT squared. Okay, and that still holds true. All right. The kind of yellowish orange triangle on the top, the displacement that occurs during this trip can be described by this 1/2 AT squared, but I have to deal with the bottom rectangle too. So for the bottom rectangle, all right, well, I know how to find the area of a rectangle. It's just base times height, all right? Hopefully by this point you're catching on a little bit about how we use the proper variables for computation in here. Okay, well, the base of this graph is time, and the height of this graph is velocity. Like this is a velocity time graph, all right? Specifically, okay, the initial velocity is the value that pertains to the height of this graph, okay? So, to compute the area of that rectangular piece, I'm going to take the initial velocity and multiply it by the time. That's my height, vi, times my base t. And this is also going to give me a displacement value. I want you to think the units of initial velocity are meters per second. The units of time is seconds. So if I take meters divided by seconds times seconds, those seconds factor out and I'm left with the units of displacement. Okay. If I take and I add together the area of the bottom rectangle to the area of the triangle, that tells me the total area that's underneath the graph. And that total area represents the total displacement, or how far the object, whatever it is that's moving here, is moved in some time period. So if I take and I write this as one full equation that has the rectangle and the triangle areas combined together, I get the total displacement for an object, okay? How far it goes when it's moving to begin with, and the way it's moving changes as it goes. Okay, and that's pretty complicated. That's also pretty important. Okay, this second equation here is important enough to where it's going to go on the front page. So just like I did before, okay, I'm going to scroll up into the top, and I have this space down here on page 1. All right, I'm going to take and I'm going to write that equation. D equals VIT plus 1/2 AT squared. All right. All right, and this is getting pretty complicated, so it's worth the time, all right, to go and try to decipher what the equation means, what it depends upon. Okay, so if I want to know where I am, that's really what this question is about. This equation tells us where am I. Okay, so to answer that, mathematically, I have to consider, all right, was I moving to start out with? That's going to make a difference in terms of how far I go. If I was moving, for how much time was I moving? In other words, how much time has passed since I started measuring? All right. And then during that time, did the way I was moving change? Did I accelerate it at all? So did I speed up? Oops. Or did I slow down? During this time. All right. These two equations here, okay, let's circle this one too. Okay, these are super duper important equations when it comes to motion, so much that I've given them my own little name. Okay, this velocity equation in red, I call that ultra mega 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 equation number 1. And this equation down here in blue, I call it ultra mega 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 equation number 2. Because with these two equations, I can completely describe the motion of an object, both in terms of how fast it's going, which way it's going, and where is it. All right, that's pretty important. At the bottom of this page 1, okay, is also a summary of the tricks that we use for the different motion graphs, okay, and why they work. All right, the slope of a distance time graph tells you speed. The slope of a displacement versus time graph tells us the velocity. All right. The slope of a velocity versus time graph tells us acceleration. All right. And then last but not least, the area under a velocity versus time graph tells us the displacement of the object. All right. So I know that's pretty complex, but we're going to do a quick example, not a quick example. We're going to do an example problem that shows how we apply these new tricks that we've derived. So if I scroll down to page number 4, okay, I have this how far example. All right, so I have a graph of motion here. Okay, and as time goes on in physics, all right, you're going to get better at interpreting these graphs both conceptually, okay, and then mathematically. All right, a physicist is going to look at this and say, without even looking at any numbers, okay, there's 3 segments here. All right, during the first segment, all right, the object moved away while speeding up. And then during the middle segment in green, the object moved at a constant speed, moving away. And then in the area in blue, all right, the object moved away while speeding up even more, all right? To compute, all right, what we're gonna do is we're gonna find how far the object travels after the 12 seconds, after the full trip. And so what we have to do is break this up into 3 chunks, okay? So that's why I have the 3 columns underneath, all right? In order to get to the displacement, all right, I am first going to compute the slope of the line, all right? So just like I did on the previous pages, I'm gonna label this VI, I'm gonna label this VF, okay? And then I'm going to compute the slope of the graph in order to find the acceleration, because we can. Change in velocity over the change in time. All right. So reading the graph here, all right, the final velocity looks like 4 meters per second, okay, where the initial velocity is 0. Okay, so change is final minus initial. So I take the 4 meters per second, I subtract the initial velocity. Okay, and I divide by the time interval. Okay, this starts at 0, so I start at 4 seconds is where I end, and 0 seconds is where I begin. All right, so I wind up with 4 over 4 meters per second divided by seconds, which means that I just have a acceleration of 1 meter per second squared. My rate of speeding up is 1 meter per second squared. Once I've found that, I'm then going to use it, okay, in that case where I find the area of the triangle using that manipulated equation of 1/2 AT squared that I found on page number 2 in the 3rd column. Okay, so I take the 1/2, I multiply by that acceleration of 1 meter per second squared. Okay, and then my time interval is that 4 seconds. Okay, so what I'm doing is I'm figuring out how far I go during this period of time. All right. So 4 seconds squared. All right, I find that if I'm doing these like mental math-wise, I actually compute backwards. So I do 4 squared first, which is 16. I multiply that by 1, and then I divide it by 2. Okay, so during this first chunk, during this triangular part of the graph, okay, as I move away while speeding up at a rate of 1 meter per second, I move a total of 8 meters, okay? That's the first chunk, so maybe we can put it like, let's do it in here. So this is 0 to 4 seconds. All right, for this middle piece, all right, my time interval is 4 seconds to 8 seconds. So we do it like that. All right, for the rectangle, okay, well, I found the area of the rectangle on page number 3, okay, which is just base times height. All right, so I just do, the displacement is base times height. Okay, if I look up at my points, okay, well, if I'm considering the green interval now, all right, this would be my initial velocity. This would be my final velocity. Okay, but they've got the same value. Like I could take and I could put the average velocity in the middle, but all of these are just 4 meters per second. Okay, final velocity, initial velocity are all equal to average velocity. These are all the same at this point. Okay, because I'm moving at a constant rate. I'm not speeding up. I'm not slowing down. In fact, the slope of this horizontal line is 0. And if you remember, the slope of a velocity time graph is acceleration. I can move without accelerating. Moving without accelerating just means you're moving at a constant speed. Okay, and so really, all we're looking at down here in this time interval from 4 to 8 seconds is average velocity times time. This is just another way of writing speed times time is equal to distance. Okay, we're using velocity because we're talking about direction, and displacement because we're talking about a distance from where we started, from origin, all right? But ultimately, it's really just a case of taking the speed of the thing and multiplying by the time frame, all right? During this middle period, I'm going 4 meters per second. Okay, my time interval is from 4 to 8 seconds, so there's a grand total of 4 seconds of time that passes in this middle period. 4 times 4 is 16. Meters divided by seconds times seconds is just meters. All right. During the middle period, I go 16 meters. During the first period, I'd gone 8 meters. And if you think about it, a triangle is half of a rectangle. Okay, so it's not so surprising that we may move double the distance in this middle period, looking at it from an area perspective. Okay, last period here goes from 8 to 12 seconds. All right, so I've got a non-zero slope. All right, I'm considering this interval, so this chunk, this little piece right here, that's my initial velocity. This here, that's my final velocity. All right, so I'm going to compute the acceleration by computing the slope. The acceleration is equal to the change in velocity divided by the change in time. All right, and I didn't expand it out before, so I think I'll do it here just so we can see it. Okay, it's not necessary to write it. Expanded out, the delta V over the delta T is perfectly acceptable. All right, as long as you know what to sub in and you've written an equation, I'm happy. All right, but I want you to see both of them, get used to them being interchangeable. All right, so let's see, what are the values of my graph? So final velocity is at 6, and initial velocity is at 4. All right, so let's go ahead and sub that in. So I've got 6 meters per second minus 4 meters per second. Okay, and my time interval goes from 8 seconds to 12 seconds. So we'll go through and do the subtraction. So I got 12 seconds. All right, minus 8 seconds. All right, so let's see. So 6 minus 4 is 2 over 12 minus 8 is 4. So 2 over 4, that's 1/2, or 0.5 meters per second squared. All right, so the point is that we are speeding up here in this third time interval. We were speeding up over here, and we're speeding up over here, but here the slope is shallower. It's not as steep, okay? So the rate at which we're speeding up is not quite as much. If you think about this like driving a car, when you hit the gas pedal, okay, you can hit the gas pedal kind of gently and only push it down part of the way, and you'll speed up. It's just going to take you longer to get up to this, whatever speed that you're trying to get up to, or you can floor it. Okay, so acceleration, the rate of acceleration can change, all right, and that's pretty neat. Okay, anyways, so I found the acceleration. Now I'm going to find the displacement. All right, this has a non-zero initial velocity, which means I'm going to go and use the full version of the displacement equation. So this is ultra mega 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 equation number 2, which is VIT plus 1/2 AT squared. All right, my initial velocity here, that's that 4 meters per second. All right, so 4 meters per second. Okay, my time interval, that's the difference between the 12 seconds and the 8 seconds. So the 4-second time period is my t. To that, I'm going to add 1/2 times the acceleration during this interval, which is that 0.5 meters per second squared. Keep my parentheses the same color. Okay, and then I've got another 4-second chunk of time squared. So this is VIT plus 1/2 AT squared. Okay, so doing the math, so I got 4 times 4 is 16. All right, and like I said, with this 1/2 AT squared thing, I like to work backwards. So let's see, so 4 squared is 16 times 1/2 is 8, divided by 2 is 4 more. So the second term, 4 meters, so 16 plus 4 is 20 meters. Okay, so that's the distance that I've traveled during each of these 3 intervals. Okay, so if I said, okay, how far have we gone during this trip of starting from rest, speeding up, maintaining a constant speed, and then speeding up some more? Okay, if I wanted to get the total distance, no problem. All right, let's go purple. Okay, the total distance, so D tot for total. Okay, so I'm just going to take those 3 pieces. I'm going to take the 8 meters plus the 16 meters plus the 20 meters, and that gets me a total distance from where I started of, what is it, that's 44 meters. And there it is, okay? Whole new set of equations, a whole new way to apply them, a whole new set of tricks for graphical analysis. That's a lot of stuff, okay? Good news is that these little equations, it's going to take us quite a while to learn how to use them and master them. Okay, this is just the tip of the iceberg. All right, and it's where we're going. All right, so go back and rewatch and fill in whatever notes you might have missed along the way. All right, and we will see you in next time.